by Professor Bernd Eppel, Director of the Institute of Energy Systems Technology, Technical University of Darmstadt, Germany. I request Professor Eppel to kindly take the stage.
My presentation today, and first of all, I would like to thank the organizer for inviting me to this very excellent conference. I'm glad to be here and give you a presentation about the carbonate and the chemical looping in coal-fired power plants. Maybe we can improve the quality of the my presentation is as follows. I would like to give you a short overview on carbon capture technologies. Then I would introduce the carbonate looping process, which is the post-combustion CCS technology, and the chemical looping process, which is the oxy-fuel CCS, CCS technology. And then finally I will give some conclusions. With this overview on possibilities of carbon capture technology, they are mentioned by my previous speaker, Mr. Topolov from UDE. There are three categories: post-combustion, pre-combustion, oxy-fuel, and the main disadvantage is that they are all linked to high energy consumption, additional energy consumption. This leads to efficiency reduction and thus energy penalty. So, and this we want to improve by moving ahead two technology. One is the field of post-combustion, which is the carbonate looping technology, and another one which is in the field of oxy-fuel, that's the so-called chemical looping, where we replace this energy-intensive air separation unit by a regular system supplying oxygen by oxidation of the metal. I will come to this later. So first generation capture technologies in the field of post-combustion, the prominent technology is amine scrubbing. The negative aspects are high energy penalties, leading to efficiency drop by 12% units. That means power plant scale of CR having 46% efficiency by applying this technology, going down to efficiency of 34% units. Another aspect is the solvent sensitivity and the degradation of the amines. Then suspend solvent, suspend amines has to be treated as waste. There's no further use, and this altogether leading to high CO2 mitigation costs, about €40 per ton of CO2. Another technology is the oxy-fuel technology. Also, this leads to high energy penalty above 10% units, and also is associated with high CO2 mitigation costs. Therefore, we all work on technologies of the second generation capture technologies, such as carbonate looping and chemical looping, and these technologies are associated with lower energy penalties, above 50% less energy penalty, and above 50% lower CO2 mitigation costs. And also we employ natural solvents, that means our spent solvent can be used as a feed for other processes such as cement industry or flue gas desalination plants. The negative aspect, these technologies are not so far developed. That means the development status of this technology is not as for amine scrubbing or oxy-fuel. Currently, we are working in the field of in the scale of 1 megawatt thermal capacity. So currently, carbonate looping works as follows. There's a flue gas from power plant. This flue gas is entering a reactor, so-called carbonator. The optimum temperature in the carbonator is 650 degrees Celsius. There's an exothermal reaction, which is described here. So CO2 from the gas starts the reaction with the calcium oxide forming calcium carbonate in some strong densities. That means even if you come here this ambient temperature, starting this reaction, the temperature inside the reactor raises up to high values, and you have to expect heat to control this temperature as a at a level of 650 degrees Celsius. That means CO2 is fixed by this reaction, is transported to a second reactor in the form of calcium carbonate. In the second reactor, there will be a regeneration of this material by increasing the temperature from 650 to 900 degrees Celsius. At this high temperature level, the reaction will go in the other direction. That means the calcium carbonate plus heat releases CO2 from the reactor, forming again calcium oxide. This is a solid material, and this calcium oxide is transported back to the carbonate. So this heat input can be done by firing fuel with pure oxygen. This is a heat input by direct firing, and CO2 will be released from the system and can be compressed or treated further. The features of the process are shown here. There's a low energy penalty. We need only 1/3, that means 30% of oxygen consumed in a oxy-fuel plant is needed here. Only 1/3 of the oxygen demand. That means we have here very much lower energy penalty. The efficiency decrease will be only 3% units without CO2 compression. Plus CO2 compression will come to a figure of 5% units. If you have in mind the figures of MEA and oxy-fuel, with their efficiency penalties above 10% units. So we are 50% lower. It's a retrofit which is applicable for several processes, for numerous processes, for power plant, also works for cement process industry, for steel production, so any kind of process producing CO2 which will be decarbonized by this process. In total, we have increased our output. I will come to this on the next slide. We can reach high CO2 capture efficiencies, which we have shown in our test. And the solvent is limestone, which is the natural solvent. It's cheap and widely available material. You find all over the world limestone. And this process is associated with very low CO2 avoidance costs. So that's the setup of a carbon looping retrofit behind a power plant. That means you have matching the power plant is here in front. That's the end of the flue gas train. There's an FGD, flue gas stabilization unit, ID fan, and then the carbon looping process starts. That means we direct the flue gas to the carbonator. CO2 will be fixed in the form of calcium carbonate, will be transported to the calciner, and flue gas from the carbonator will be released without CO2. And in the carbonator, in the calciner, we use a regeneration by firing fuel with oxygen coming from 650 to 900 degrees Celsius, thus releasing CO2, and calcium oxide is transported back to the carbonator. So the positive aspect is that we work at very high temperatures. That means in one reactor, the temperature is 650 degrees Celsius, in the other reactor 900 degrees Celsius. That means the flue gas temperature or off-gas temperature has also 650, 900 degrees Celsius. That means we can utilize this heat at a very high temperature level to produce high temperature steam and thus to produce electricity in a steam turbine. That means this retrofit is associated with an additional electrical output of 50%, referring to the reference power plant. That means if we retrofit a 1000 megawatt electrical power plant with this concept, that means we have another 500 megawatt electrical output from this carbon looping retrofit setup. So at first we did feasibility studies. The results were very promising. We did some lab scale testing, some numerical study, and we were involved with projects, and with this project we were able to build our own building. That's a building where inside these test tubes are located. Outside you see technical gases, with CO, O2, CO2, with their own transformer for the electricity, and inside this building we have performed the test, and now we have an operational hour of more than 2,000 hours. So these are the main vectors. These are CFE vectors, that means circulating technologies. There are two vectors. CFE 600. 600 refers to the inner diameter of the unit. The unit is a refractory line. That means the outer diameter is 1,300 millimeters. The height of the vector is 9 meters. And there are two functions. That means we work with these two vectors for carbonate tubing. For carbonate tubing, this function is the carbonator, and for chemical looping, the function is the fuel vector for this. For chemical looping is the air vector for this CFE 600. CFE 400, having an inner diameter of 400 millimeter, also reflector lines. Several outer diameter of 1,000 millimeter, it is 11 meter. Function of this second vector is the 400 is the Kaltzheimer for carbonate tubing and the fuel vector for chemical. That's a setup for megawatt setup for carbonate tubing. There's a coal combustion purified furnace with capacity 1 megawatt, producing a typical flue gas. And this flue gas is directed with the carbonator, and carbonator can be also operated with synthetic flue gas. This was our first step. We worked with synthetic flue gas, capturing CO2 inside the carbonator. We can extract heat with a flexible heat exchanging system out of the carbonator to maintain this optimum temperature of 650 degrees Celsius. Then decarbonized flue gas is transported by a heat exchanger, filter, and then towards the state. So CO2 is fixed in form of calcium carbonate. Carbonate is transported to the second vector, the Kaltzheimer. The Kaltzheimer is fired with coal and the O2, and you can also add the CO2 and steam. And in the Kaltzheimer, the direction is going in the other direction. That means the calcium carbonate releases CO2. CO2 is released is the off gas, is directed by a heat exchange filter, and with a heat fan towards the So this is a setup where we perform the test. So that's a photo from the unit when we start operation. So we start the first fire inside the unit in August 2010. That's the rise of the CFE 600. That's the startup terminal, and we deassembled the nozzle plate. It has the possibility to look inside the unit. That means normally this nozzle plate is fixed to the bottom, so we open this and we put in a camera to watch the startup process. So now the ignition burner starts, and then the startup burner coming into operation is a final capacity of 700 kilowatts. That means this startup process takes several hours because the material outside is refractory blind, and at a temperature level of 600 degrees Celsius we can switch to cold fire. So these are the experiments in the 1 megawatt for carbonate tubing. So by now we have gained experience with more than 2,000 hours of full-life operation. In September we did first tests with alternating CO2 capture and generation in one vector. Then 2 vectors came in operation in July 2011. At first we start firing the Kaltzheimer with propane. Another campaign in January 2012, also this campaign, and then in February 2012 we did the operation of the Kaltzheimer with coal. And on this last campaign, I will show you some representative results. So you see the flow, the flow, the temperature, pressure inside the carbonator. That means at the bottom of the carbonator, that's the CO2 flow rate in kilograms per hour. That means here we start getting CO2. That's the temperature inside the carbonator. Remember, the optimum temperature is 60 degrees Celsius. That means when we start this process, the temperature raises strongly because the reaction of hydrogen oxide plus CO2 is highly exothermal. That means we have to insert our heat exchanger to control this temperature level to 60 degrees Celsius. And you see the pressure inside the reactor in millibar. It's the pressure cap at the bottom of the reactor, which represents the particle load, the solid material inside the system. That means we see an increase in pressure because there's a formation of calcium carbonate, which has a higher molar weight. And we see the CO2 absorption inside the carbonator. That means the goal is 80%, which has been reached for a long period. 80% CO2 capture rate inside the carbonator. The calciner has a nominal CO2 capture rate of 100%. That means carbon entering the calciner will be released as CO2. That means we have 100% CO2 capture rate inside the calciner. Taking this together into account, we come to a total CO2 capture rate of 90%. Maximum was after 90%, 93%. So another parameter has been tested. So if we decrease the temperature down to a level below 60 degrees Celsius, as shown here, also the CO2 capture rate inside the carbonator is goes down. So the message is that they need to do everything to keep this temperature level at 60 degrees inside the carbonator. So here the concentration inside the calciner. We have the oxyfuel calciner, that means we add the O2, it's inlet of the calciner together with the CO2. So the performance of the process is very good, excellent, but still we need oxygen for this calcination process. It means we burn both with oxygen. This is isolated to to efficiency drop of 3% unit, which is really low compared to other technology, MEA and oxyfuel. But if you want to further reduce this energy penalty, you have to get rid of the employment of oxygen. And this can be done by indirectly heated carbon looping process. That means now we do not transfer the heat as done in the standard carbon looping process by firing coal with oxygen. We replace this system by a heat exchanger. That means this heat exchanger is heated with a combustor firing normal air, ambient air with fuel. The heat is directed inside the calciner, and the off gas from the combustor is directed to the carbonator, where we decarbonize this flue gas produced in the combustor, and we decarbonize flue gas from the reference power plant. We have done studies on this, and we do currently the erection of a 300 kilowatt indirectly heated carbon looping test rig, and the beginning of 2014 we start operation of this 300 kilowatt unit with a rate of 10 liters. And the efficiency penalty is below 1%. So coming now to, by now we have done, we talked about post-combustion, carbon looping process. Now let's look at oxyfuel process. This demand for oxygen, which is supplied by air separation unit, leads to a high energy penalty. and this air separation unit is replaced by a special reactor system, which is shown on the next slide. So the air separation unit is replaced by a reactor, so-called air reactor, which is also a circulating fluidized bed system, which is operated at a temperature level of 1050 degrees Celsius, using ambient air leading to a reactor. Inside the reactor we have an oxygen area, a natural oxygen area or level, which is oxidized at a temperature of 1050 degrees Celsius, and this metal oxide is supplying the oxygen to the reactor. That means we do not need an air separation unit. We replace the air separation unit, the cryogenic air separation unit, by this air reactor, extracting the oxygen out of the air, and at the end we have nitrogen, which is relieved from the air reactor. So the fuel reactor is operated as follows. We use fuel, coal, hardcore lignite biomass, and we use recirculated off-gas, especially steam and CO2 is important. That means the fuel will be gasified inside the fuel reactor at a temperature level of 970 degrees Celsius, and the gaseous products from this gasification process will react with metal oxide, forming CO2 and water steam. And this process is associated with a very low energy penalty. So 1% unit without CO2 compression, this CO2 compression, we come to 3% units efficiency penalty in the top. So we use a natural oxygen carrier, which is ilmenite. It's iron titanium based material. It's widely available, very cheap. So 1 kilogram was 10 euro cent. And the process is associated with low CO2 mitigation costs, around 10 euro per ton of CO2. That's a very much simplified setup on the chemical looking process. There are many other devices which I deleted to make it more transparent to explain. These are the main reactors. So one is the air reactor, so we use ambient air, and the metal is oxidized at a temperature of 1050 degrees Celsius. This is the exothermal reactions, that means we have to extract heat. At the end we have oxygen-depleted air, it's nearly pure nitrogen, and the metal oxide is transported to the fuel reactor. In the fuel reactor we add coal plus water steam and CO2. The coal will be gasified, and the gaseous species will react with the metal oxide, taking the oxygen from the metal oxide, and the reduced metal oxide plus char is transported to the air reactor. So in between we have a carbon stripper to separate the char from this solid flow, and the char will be transported back with the fuel reactor. That means we have mainly reduced metal oxide, which is transported to the air reactor, and again to be oxidized. I think this is a closed loop. The metal is heavy. You can imagine we have 5,000 kilograms per cubic meter of density, so it's easy to keep this metal inside the circuit. So at the end we have CO2 and water steam in the ideal case, but in the reality we have some unburned gaseous species, which will be oxidized with oxygen in a post-oxidation chamber, and at the end we have CO2 and water steam, which is transported to the stack. So these are some first results. So we have done 30 days in 3-shift operation. We used typical import coal, ambient coal. The air reactor has been operated at a level of 1000 degrees Celsius. The fuel reactor has been operated at 900 degrees Celsius. The fuel reactor was operated utilized with steam and CO2. And that's the air ratio which has been used. It means in the ideal case we use 100% oxygen from ilmenite. So this we could not manage in the first investigations. So we have to add 10% oxygen from air. Therefore the air ratio is 0.1. I mean, in the ideal case, so the ultimate goal would be to have here air ratio of 0. So we have to live with this 0.1 at that time. So 0 is the ultimate goal. That means all the oxygen is coming from the ilmenite. So these are the that is gaseous concentration. It's the outlet of the reactor. In the ideal case, we have CO2 and water steam. In reality, we have some unburned gaseous species, such as CO, hydrogen, methane. These are the concentrations, but if you look at the scales, these concentrations are very low. That's the methane concentration, so the range of 1%. This is the CO, this is the hydrogen, and this has to be burned inside the post-oxidation chambers. That means the oxygen demand is at the moment 20% for post-combustion is oxygen, post-oxygen pollution. So ideal case would be we have low CO, low methane, no hydrogen at the other spectrum, but in reality we will have some, at least some traces of these components said to be oxidized. Yeah, let me conclude the carbon looping process. There's a continuous CO2 capture test, our 1 megawatt carbon looping pilot plane. The presented campaign is stable operation. As either was fired with coal. We could show that we can reach very high CO2 capture efficiencies, 80%, above 80% CO2 absorption in the carbonators. That was a goal. And 90% total CO2 capture rate if we take into account carbonator and oxy-fuel fired calciner. And 90%, this is also CO2 capture rate which can be, which will be achieved with other processes such as MEA processes. So there were 100% CO2 capture rate in reality. We could also show a strong dependency of CO2 absorption in the carbonator or temperature. That means if we go down from the optimum level of 650 degrees Celsius, so down to 600, so this deteriorates. So it is a must to keep this temperature control of 650 degrees Celsius and have a good CO2 capture efficiency. For chemical looping, we have done successful commissioning of chemical looping plants. First operational results are very promising. We continue within the follow-up project. It's the Acclaim project. Next year we do further tests. We want to modify the 1 megawatt plant and optimize some areas, and then we start operation next year. So in total we reached more than 2,000 operations in 3 road and covered operation. So this project has been funded by the EU. There are 2 possibilities. One is the research fund for the steel, the Carina process. This carbon capture by indirect heat combination process was funded by the research fund for the steel. The money coming from the EU. The Eclair on chemical looping, which means the emission-free chemical looping for combustion process, was also financed by IGCC. And currently we execute the Acclaim project. This is also funded by the research fund for the steel. There's another new project called Success. And for limestone, we have performed a large project which has been funded by the Federal Ministry of Economic, by the German Ministry of Economic, means the limestone-based absorption of CO2. So this has been done together with industrial partners. So we have a strong industrial support by companies, Alstom, BSF, E.ON, Pisa, of one-time Hitachi, Rust, Intel, RWE, using both Anfall, they supplied us with their expertise, technical expertise, also with money to be able to perform these tests. Yeah.